Hello, this is G. Om Kedareshwar Kiran from Electrical and Electronics Engineering Department. Today the topic is about dynamic performance analysis and permanent magnet synchronous motor. This dynamic performance analysis of permanent magnet synchronous motor in depth. They Synchronous motor is nothing but it matches the field of the stator and the rotor. The revolution of the stator magnetic field and the rotor revolution is at the same speed. Then it is called the synchronous motor. This represents dives into dynamic performance analysis of permanent magnet synchronous motor (PMSM), exploring their operating principles, key performance matrices, and advanced modeling techniques. We will analyze real-world performance challenging and delve into case studies highlighting PMSM applications of high-speed scenarios. Finally, we will discuss future trends in designing recommendations of optimizing this performance analysis of permanent magnet synchronous motor. Let us go in depth with these motors. Fundamentals of permanent magnet synchronous motors, operation and design architect. These PMSM operation utilize permanent magnet to create a rotating magnetic field. Generally, in three-phase, we are having the rotating magnetic field interacting with a stator winding to produce torque. The rotor containing permanent magnet rotates in synchronous with the magnetic field, enabling efficient energy conversion. In this design and architect, this permanent magnet synchronous motor design incorporates a key element like a stator winding rotor with permanent magnets and a housing with the stator winding carrying current, generating the magnetic field. The rotor typically compressed between rare earth magnets. Generally, the gravitational is between 9.8, providing the permanent magnet field or the torque generation. Generation of torque is generally happen in the design of architect of this uh, permanent magnet synchronous motors. Now coming to key performance matrices efficiency, torque and speed analysis. 90% of the efficiency measures the motor's ability to convert electrical energy to mechanical energy. It influenced by factors like design, operating conditions and losses. In this key performance and speed analysis, the Newton is torque equal to Newton in Newton per meter. Then if we take 100 Newton per meter torque is rotational force produced by motor. It critical for applications requiring high starting torque and maintaining consistent load. If the load is greater than the resistive load, the motor may damage. And nearly 10,000 rpm speed represents the motor rotational velocity of permanent magnet in synchronous motor, achieving high speed due to their unique design and magnetic field of interaction. This unique design may help us in the magnetic motor efficiency to run in a synchronous speed. The key performance of this efficiency, torque and speed analysis, the efficiency should be 90%, torque is 100 Newton per meter, and a rotation per minute is 10,000 rotations per minute with a speed of 10,000 rpm. Now to advanced modeling techniques for dynamic performance evaluation. Performance evaluation, finite element of analysis, helps us to analyze the magnet field distortion and optimize the motor design for maximum performance. Electromagnetic transient analysis, this stimulates the electric transistor behavior of the motor under the dynamic condition, providing insight into electromagnetic forces of voltage and fluctuations. System level simulation. The system level simulation integrates the PMSM model with the control system and their component to assess overall system performance. In the right side, we can see the motor induction motor diagram. There are terminal box and stator and rotor winding. and the different gauge and scenarios of the rotor and stator copper windings and slots. The outcome is a shaft. The system level simulation. In the element analysis, there are different types of slip rings, and the motor, induction motor, accordingly it will run. These are about the performance and the dynamic evaluation of electromagnetic transient analysis, ETA and FA. The system simulation is followed through the control system of other components, as overall system performances depend on the induction motor. So, in these different scenarios, thermal management and cooling system optimization. If the why the thermal management is important. Thermal means nothing but it is an heat generation losses with the motor, including copper losses and core losses, generate heat. Copper losses are dependent on the current, and the core losses dependent on the voltage, generate the heat. So the loss within the motor, including copper losses and core losses, generate heat. Heat transfer. Heat is transferred through conduction, convection, and radiation. This process needs careful analysis of prevent overheating. Then coming to the cooling system such as the air and or liquid cooling and employed to dissipate heat and maintain optimal operating temperatures. Next one is optimizing. Optimizing cooling system design involves finding the most efficient heat dissipation or method of the permanent magnet synchronous motor application. So the synchronous motor is nothing but the stator magnetic field and rotor rotates at the same speed. Then it is called the synchronous speed. Then according to the induction motor running principle, the heat generation, heat transfer, and all the other cooling systems may differ with time variant responses. These can be generated with managed with cooling system of optimization. Now coming to the real world performance challenges and solutions. Torque ripple the ripple factor is mainly what we call fluctuated in the induction motors. The ripple factor, torque ripple factor is main, as the torque ripple is a fluctuating in torque leading to vibrations and noise. Solutions include optimizing magnet placement and using advanced control techniques. These torque ripple and the voltage fluctuations can be affect the motor performance. Solutions include employing a reboost control system and filtering, filtering techniques. These voltage fluctuations mainly caused because of the core losses. And the thermal management. Finally, the thermal management, maintaining optimal operating temperature is crucial for longer time and performance. Solutions include efficient cooling systems and heat skin design. The skin is nothing but the outer frame of the induction motor. The thermal management, maintaining a cool temperature is crucial for the longer time performance of an induction motor. So these are the real world performance challenges of and solutions of the induction motor, whether it is a synchronous or asynchronous induction motor. Generally, the induction motors are asynchronous. If it rotates with the synchronous speed, then the slip becomes zero. If, for example, the stator magnetic field is 1500 rpm, thinking that it is a four-pole induction motor, then the stator will rotate at 1440 rotations per minute, 1440 rpm. Then the slip equal to 60. Generally, the slip formulas, percentage of slip equal to nr minus ns by ns. Ns represents the synchronous speed and nr represents the rotor speed into 100. Since we need in the percentage, it is calculated through 100, and the slip equal to 60%, means 0.06%. Case studies: higher speed permanent magnet synchronous motor applications. These are used in the electric vehicles. PMSM, permanent magnet synchronous motor, are used in electrical vehicles powertrains, delivering high power and torque for smooth acceleration and efficient driving. High power and torque is necessary for the more acceleration and efficient driving. Industrial automations, high speed PMSM are em- employed in robotics, machines, tools, and other industrial applications requiring the precious of fast motion control. And aerospace PMCS applications are aeroscrafts and system aerospace higher reliability and permanent. Then the case study of higher permanent magnet synchronous motor applications are electric vehicles, induction motors, and aerospace. In these three, these are the three applications of high-speed induction motors with running with a synchronous speed. And next one is finally the future trends and designs recommendations for enhanced performance. Advanced materials, exploring new magnet materials with higher energy density and improved temperature stability and enhanced motor performance. Artificial intelligence, AI. Learning AI is an optimization of PMSM design with control parameters, enabling adaptive and efficient operation. For the AI generation, AI is artificial intelligence. It learns the uh, motor behavior, and accordingly it will adjust the optimization of synchronous speed. Multi-phase simulation, developing comprehensive multi-phase models, integrated electromagnetic, thermal, mechanical aspects, and accurate performance predictions. This can be in the different way of multiple physics simulations. So these are the future trends and design recommendations for the enhanced performance. Thank you.